too much sense to go through all these menus and stuff. So this is really not, I mean, you can learn it. It's described in the manuals and the technical manual and everything. So I will just slowly do things, okay? Very, very, very slowly. And so it's learning by doing, okay? So what we have to do is, first of all, we have to load in the powder pattern. So the task for this first session this morning is to get in different ways the instrumental resolution function, yeah, because it's the first thing you have to do. And just as a reminder, if you have your instrument, the instrument you're using at home, yeah, make sure that in regularly time slices you measure your standard. So typically, if it's a Bragg Pentano instrument, you measure your lanthanum hexaboride. If it's the Dinnebier instrument, yeah, and if it's copper, lanthanum hexaboride is not such a good idea. Then you have to live with typically either some garnets or some silicon, yeah. But if you have, let's say, a Dinnebier instrument with molybdenum radiation or silver radiation, then of course it's lanthanum hexaboride. And it, depending on how far you want to go, it really makes sense to use the NIST standard. The reason is because this has been really, really certified to a couple of digits after the decimal point, until the point where the temperature in your lab plays a role. Yeah. So if you really want to know exactly how your instrument is functioning and how good it is, and if there are any problem, yeah, then you should of course not refine the lattice parameters of lanthanum hexaboride, right? Because you should keep them fixed, and then you can see or even the tiny little problems in your instrument. Okay. So what we do here now is we load now in some powder pattern, and for today, actually, I decided to use another. So for years, I'm always using this nice Bruker high-resolution pattern from the Bruker machine with the molybdenum radiation, so germanium 220 monochromator, but today I think we use a different one. We use... So we load the scan files. You see files, the first top-down menu. We load the scan files. And then IRF. And we have to select the data format. And you see the standard data format, of course, because it's related to Bruker, is raw, the raw format. But this one is just ASCII. Yeah, it was a very simple store machine. So I select this because the geometry is so simple. Yeah, so we open here the pull down menu, and you see there are many different file formats, and the most simple one, of course, is XY, 2 theta intensity. That's it. All right, and so I opened the one here which is called IRF. It's in the exercises bar, in the BARI subdirectory, IRF for instrumental resolution function, and this is called store molybdenum Dinnebier, yeah, store molybdenum DS. So this is a powder pattern, and this is the powder pattern here of the lanthanum hexaboride. And I'm using this to really show you how important it is to measure far out. Yeah, so this is molybdenum radiation, and if you go out to the pattern here to 110 degrees, then the despacing will be something like 0.5. But of course, the system doesn't know the wavelengths because it's ASCII data, right? It's just X and Y. So the first thing we have to tell the system, of course, is what wavelengths we are using. And now you see how the whole thing is structured. It's from top to down. It's a tree menu. The tree menu means you have some global parameters on top, and then the next layer is your data sets. It could be one data set, what we are now doing, or it could be 200 or 5,000, right? Everything is possible. But so the next layer is the data set. Then in the data set, there are the global parameter for this particular, or the local parameter for this particular data set. And then, of course, there are structures or polyfits, which means refinements without structure, or peaks phases. Yeah, so this is the layers down. And then in these peaks phases, in these structures, there's the atomic coordinates, and so on and so on. So it's really a tree structure, right? And so since we only have one pattern, so our tree structure will be here now shown as the first powder pattern on the top. And if it's active, yeah, you see this little square is filled. If I click on it, now the whole thing is inactive. That means you can load in, and this is something I use a lot, you can load in hundreds of data sets, and just declick them at once. So there's a possibility to do it. And just because in particular, if I want to compare data sets and then I click the 10 or 20 I'm interested in and compare it to my original data, it's very useful. In particular, if you do some pharmaceutical work, okay? So I have a set of, let's say, 300 data sets. I load them in all at once, but if you see 300 data sets on the screen, you basically see nothing. Then you load in your new data set, and then you can actually click them on step by step. And those which are clicked on will be subjected then later to the refinement. Okay, so this is clicked on. And when I go to this tree structure to the left, no idea if you can see it on the little screen here, then you will see the next layer pops up. And this is what you need, the minimum, which is the emission profile, because you have to know what's coming from your from the X-ray tube, or in case of synchrotron radiation. And then we have the background, the instrument, some corrections, and miscellaneous. So we start with the emission profile, okay? And the standard emission profile, of course, is what 90% of the users use. It's a K-alpha-1, K-alpha-2 copper, distribution. And the way it's done in TOPAS, it's a little bit interesting, but of course it makes sense. You see, the way it works in general is that you have something called values, and the values are displayed here in this field here. And there's the area, the wavelengths, the half width, and some other parameters. Okay, and the area is clear. I mean, if you load in your peak profile from the tube, the sum of all contributions, must be 1, right? You don't want any intensity contribution from your X-ray tube. So the integrated sum of the peaks must be 1. And you see for the K-alpha-1, K-alpha-2, it's 0.65 and 0.35. So this is 1. Okay. Then you have the wavelengths. In this case, it's copper K-alpha-1, copper K-alpha-2, and the half width. And with this particular peak profile, it's only using Lorentzian peaks, 2 Lorentzian peaks, and they have a very strange unit. It's milliangstroms. And the reason is you want, I mean, like always, humans want numbers between 1 and 10. Guess why? That's your fingers, okay? You feel more comfortable if the numbers are between, let's say, 0 and 10, and you don't like numbers like 0.000137 or something, right? Or 10,999,780. Yeah, you want these numbers, and this is why he uses milliangstroms. So don't get scared. Just very quickly, you will see this on and on and on later. The way TOPAS works, there's next to the values, there's something like codes. And if you go into codes, you see all these values can be subjected to refinement. If it says fix, they are fixed. If it says refine, they're refined. Also refinement, if it's a little at symbol, also means refinement because it's not really consistent in TOPAS. Maybe you should tell Alan that he should make it consistent in the whole thing. But it's either at or refined. I mean, you get used to it, right? What also is important, because we need this later, you can also, and this is one of the many nice things in TOPAS, you can put in a variable name. If I put in a variable name, in the codes, I can give it my own name. I can say hi or hello or Robert or wavelengths or whatever I want. I can put it a name, and then this name is a variable in TOPAS. And it will be refined unless I put an exclamation mark in front, then it's fixed. And why is this nice? It's not only nice that you then have this variable available, you can also use it in all kinds of equations. And these equations can be arbitrarily complicated. Even if it doesn't make any sense, you can say, the wavelengths of the second pattern should be the wavelengths of the first pattern plus 0.1 times the tangent of square root of something, okay? Doesn't make sense for this example, but would make sense if you have different occupancies. If you have 2 elements on the same side, you can say, this is iron and cobalt, so this is occupancy of iron is my name, and then the cobalt is 1 minus the occupancy of iron. And then in addition, I can also say, oh, the minimum of the values is 0 and the maximum is 1, okay? And this is what you see here. So there's minimum and maximum. So you can type in these numbers. There are lots of options. We are not going through this right now. And there's something called errors. Errors means ESDs. Yeah. If I want the errors, I have to tell the program if I do any refinement, I want ESDs, at least the statistical ones. And in order to to get them, I think they are not in there by default. You have to go to the so-called fitting options here, which is this little button, and you have to click calculate errors. And I also do something because I want to show you step by step how to get the instrumental resolution function. So I don't want the system to refine the entire powder pattern at once. We are now picking peaks, yeah. So I tell the system fit zoom, just fit what I personally zoom out. If I zoom the entire powder pattern, yeah, out zoom it, then it's used. If I just use one peak, yeah, then I can use only the zoom part. Remind me later that I unclick this, okay? Because later we want to do the whole pattern fitting, and it's yeah, I should remember it should not be the zoom part, okay? All right, so first of all, I set emission profile. That's of course wrong. This is copper KL412. We have molybdenum. So in the emission profile, you see now, if you click on this tree structure on the emission profile, there's another window below, which gives you some, excuse me, gives you some options. And one option is load the emission profile, okay? I mean, it's very rare cases you will actually make your own emission profile. It makes sometimes sense if you have a very, say, special instrument, yeah. But usually you can select one of these, which is perfectly okay. And then a menu opens, and in the menu there is lots of options. And there is molybdenum. Unfortunately, there's only molybdenum K alpha 2. So if I click this, oops. All right.
Alpha 2 is not values here. 2 is spider web.
Oh, sorry. Here we go. Yeah. Oh my God. Yeah, getting old. So now you see this is molybdenum K alpha 1 and K alpha 2. Okay, but we only have K alpha 1 because it's the primary beam monochromator. So the instrument is very simple, right? This is there's an X-ray tube, and the beam goes to a Johann monochromator, yeah, as a germanium 111 or Johann monochromator, and then from there it is actually focused through the capillary on the detector. And the detector in this particular case was 3 Mythen or Meissen detectors, okay? So 3 detectors, 18 degrees wide, so we cover a big range, so we don't need long measurement times, okay? So it's a very simple instrument. So the only optical elements we have in there is there is some divergence slit, but it doesn't really cause any problems because it's focused anyway, yeah? And actually the slit is wider than the beam. And then there is, of course, the detector. And the detector consists of silicon strips, and each silicon strip is basically acts like a receiving slit. Because in theory, which is not really the case, but in theory, the strips of the detector are independent from each other. So each strip acts as its own receiving slit. So we can mimic actually, with the parameters, we can mimic the receiving slit width by the width of one silicon strip. We know this approximate is about 0.1, 0.11 millimeters. So it's a very, very simple thing. So what we have to take into account will be only the wavelength distribution, the receiving slit, and of course we have, it's a flat detector on the focusing circle, which means we have some parallax effect. But for now, we have to fix the wavelengths first. So in this case, the K alpha 2, we got rid of. So you can mark this line and somehow press delete. Oh God, on this computer, where's delete? This one? Okay, good. Nope. No? Nope.
Command delete.
Sorry? Commands delete. Okay. Command and then this one?
Yeah.
Oh yeah, perfect. Okay. Delete section. So now it's gone. So now you tell me, what do I have to change here?
The area.
The area, right. Very good. The area is 0.65. It doesn't really harm because it's relative intensities, but you don't want any artificial contributions. Yeah. So we have to change this to 1. So we make a double click in here, It's a 1 and fine. We are not changing the half width. It's probably right. Yeah, we don't know it exactly. It might be 0.25. It might be 0.28. So this is not really. And as I said, you can measure your instrument. It's a very complex procedure. You can do the fitting, and then you know exactly the values. But this is probably okay. One thing which is important here is the Y min on Y max. Yeah, it says 0.0001, which means the peaks are calculated until the intensity from the top is down by 1/10,000th. Okay, yeah. If you really want to do an extremely good job and have a very high peak and very small peaks, you can even make this number a little bit smaller. We can put another 0 in here, but we don't have to. Okay, so now it's 10 to the minus 5. All right, so that's all. So the instrument is fixed. So that means we can actually go to the next one, which is the background. And the background, the default background in TOPAS is a Chebyshev polynomial. These are orthogonal polynomials, which are just a little bit less correlated, the parameters, than for the normal polynomials. Yeah, but okay. But they are, of course, they are correlated. And that means if you have a complex background, what you not should do is adding more and more and more parameters, because then the background starts fluctuating. Yeah, but this background which we have here is so beautiful. The only thing we see here in our pattern is that there is down here, and there is from the glass capillary a little hump. Okay, so probably the glass capillary later, when we do the best job we can do, we can model it by a broad peak, and then we can keep the number of background parameters extremely small, maybe 3 or 4. Yeah. But for now, we don't care. We just say linear background because I want to just refine a single peak. Okay? All right. So if you see order 1 means this is actually how many parameters? Order 1 is linear, so it's with 2 parameters, right? It's the constant part and the linear part. And if the background, for example, typically in the Bragg-Pantano machines, if you use a big open detector, position-sensitive detector, you get a lot of air scattering. Yeah, and air scattering is, as you know, forward scattering, so it's just going to low angles, and then you have this background going up, and then the normal polynomials don't work very well, so you need also another term, which is x to the minus 1 or 1 over x. Yeah, and this is actually this 1 over x background. If you click this one, you can actually model the air scattering. Here we don't have the problem because we were blocking this by some, I think there's some big tungsten beam stopper. But so we leave it for now, we leave it at 1 because we want to look at single peaks. Then we go to instrument, and instrument, there are so many things. I cannot go through this in detail, okay? Otherwise we are sitting here in an hour. But since we want to do fundamental parameters, we just focus on the correct numbers. Honestly, I think this is not correct. So the primary radius and the secondary radius for my instrument are a little bit different. I think it's around 230. Yeah, I'm not 100% sure, but therefore I just 270. Yeah, it's also okay. Probably it's correct. I haven't measured it recently.
Unless you ship the development.
Yeah. So but it's a Stoa device. It's also it's clear for the Bruker one, but this is now a Stoa, and I think it's a little bit different. I think it's 230 or 225 something. Don't ask me. But we leave it there because if the numbers are a little bit wrong, it has lots of effects. It's just changing the fundamental parameters, just shifting these values a little bit. Yeah. And so it's not causing big problems. We say for now it's a point detector. I mean, again, these are 3 18-degree detectors, so there are thousands of silicon strips, and each of them acts as a single detector. So we leave it like this. We know that the receiving slit is about 0.1 because I think the distance is 0.11 when I remember correctly. We are not putting it in here because we want to see the effect of the wavelengths first, and the rest we just forget here. And then, of course, we have the actual convolution, which is giving us a strong asymmetry. And you can see here, if let's, for example, take the first peak, there's quite some strong asymmetry because at 9.5 degrees, we have a small Dinnebier cone and we are cutting it, and if you don't like it, if you want to get rid of it, sure, it's possible. I mean, you can make some slits in front of the detector, make it very, very, very small. Then you have basically no intensity, but then you have beautiful peaks. Or you say it's a pure geometrical effect. I don't really care. I make it open. The peaks look ugly, but I can model it. Okay, so it's your choice. All right. Just to give you a feeling, there are so many other things. For example, additional convolutions here, and we will use this later. Then we go to corrections, and the corrections, of course, when we do the full pattern refinement, we need a zero shift. Yeah, because every instrument, no matter how good you align it, there's always a small zero shift. I mean, if I do the best job I can do, and I wrote a routine for this, a big macro, I can go down to 0.002 of a degree, but that's about the bottom line. Usually the zero shift is about 0.01 or something. We have sample displacement. It doesn't play a role in the capillary. There's the Lorentz polarization factor. That's actually important. The value you put in here, if you have a normal instrument without monochromator, the value is 0, which means it's unpolarized radiation. What's coming out from your tube is unpolarized. If you go to the synchrotron, your beam is almost 100% polarized. It's actually not 100%. We measured it's about 88, 89, 89.5, but who knows, right? So we say it's 100% polarized, and so the angle, the polarization angle, is 90. If it's 90 degrees, means 100% polarized. And if we use a primary or secondary monochromator, the value which goes in here is the angle of the monochromator. All right, and the angle of the monochromator we are using for molybdenum K alpha 1 radiation using a germanium 111 Johann monochromator is 20.5 degrees. There are scripts which help you calculating it, and there are also lists for most of the instruments. I have a couple of exotic instruments. I have 14 powder diffractometers, so there are a couple of very exotic ones. Okay, and so some are not standard, and then we have to calculate them. This one is 20.5. All right. We don't care about these things, absorption and so on at the moment. Then there's miscellaneous here. And miscellaneous tells you if you want to do the whole pattern, where do you want to start, where you want to finish. You can put in a couple of values. You can calculate degree of crystallinity. There's so many options, So read the menu is not what we need today. What we now want to do is we want to fit one peak. We want to see, do we get a good fit of one single peak? And let's use the first one, which really looks ugly. And now we want to see what's the contribution of the wavelengths to this peak. So what we need is we have to put in a peak. So this little box here, I can put in a peak. I just go in the peak, click, and then I turn this off. And you see now there's a peak. And oops, there's a peak's face. That's what I say, top-down menu. So it's going from, it's a tree structure. So as soon as I included a peak, there's another layer that says peak's face. If I would include a structure, it would say, structure phase. If I would include the polyfit, it would say HKL phase. Just an odd name, but you get used to this one. So we go to the peaks phase, and then the same thing. You have values, you have codes, you have errors, you have minimum, maximum. You get a lot of information from this peak if you assume that this peak is exclusively responsible for your domain size. There's no other effect. Then you get the values here, or if it's only strain, or if you have both things, but both things you cannot get from one peak. You need the entire powder pattern. But for now, the only thing we want to refine is the position, the area, but not the crystallite size, because we don't want to add anything. So we go to codes and unclick the crystallite size. And now that's all we want to do. So now we can do a fit of this peak. And this is the fit. And the difference curve looks ugly, so I unclick the difference curve. I don't want to see this. And now I blow this up, and you see the blue line is what we have measured. All right? The red curve is actually the contribution coming exclusively from the X-ray tube. All right? Good. So that's fine. And you see the fit is excellent, right? Is it correct? Not so really excellent, but we can do something. Okay, so the next thing to do is probably, we know that there's a receiving slit, okay? Receiving slit is a rectangular function. Yesterday I told you, and hopefully you remember for the exam later, how to calculate the convolution functions from the Fourier, right? Just kidding. Okay, yeah, so you should remember if you have a convolution of a rectangular slit function, and in this case, this is a Lorentzian function coming from the X-ray tube, it will be a slightly odd-shaped broadened Lorentzian function. So we go back here to the instrument and say, oops, yes, receiving slit width, I think it's 0.1. It's 0.11 something. I just leave it at 0.1. Okay, good. Now let's see what's happening if I do the refinement again. Booms. Oh, it's broadened. Interestingly, if I blow this up here, you see it looks a little bit strange, yeah, because but it's a broadened Lorentzian function here. Okay. If you want more points because it's a very sharp peak, you can go to miscellaneous and say convolution steps. Now I think 2 is better. If I now do 2 convolution steps, then the whole thing looks a little bit more smooth, you see? A little bit more smooth. Oh yeah, I could maybe do 3 or 4, but it's fine for the moment. All right. Convolution step means how many, it uses the step width, but if you have a coarse step width, and this is relatively coarse for this very sharp peak, yeah, it's probably better not to calculate at every step your calculated pattern, but also a step in between. Makes your function a little bit smoother. If you use high resolution synchrotron radiation, this value should go up to 5, right? Because otherwise you see only lines. But okay, did it solve our problem completely yet? No, not really. So now we have to go and put in some numbers from the actual divergence, and we can use the full actual model. And the values, honestly, I don't have them exactly. I think they should all be around more or less 8. But since the values are not correct from the radius, these will change a little bit. And also you should know these are 3 values. Yeah, you see this is the source length, the sample length, and the receiving slit length. They are 100% correlated. So you can refine 2 parameters, yeah, and keep 1 fixed. If you refine them all, which is okay, yeah, there's 100% correlation, so the numbers are not that meaningful, but you want a good fit, and I think this is all we can do. So let's see if I put in 888 for now, what it does. Oh yeah, not so bad, okay? But not really good. But yeah, it's almost fitting this. And probably I can refine the outer 2 and see how this goes. Oops, yeah. I'm not 100% happy, but almost. So it's 11, 13, 8. If I now refine the third one, it might stay there or not, but you will see it's a tiny little improvement. No, it doesn't want to change it. That's something interesting in TOPAS. There's a positive and a negative side. TOPAS is highly sophisticated, and if TOPAS figures out that a value you're going to refine, it's not a good idea to refine it because of extreme high correlation, because it would actually blow up to refine something, then it stops it automatically, which is in 99.9% the cases great. In 0.1% of the cases, you want to see what's happening. Yeah, so be careful. But I think it's a great thing. You see, it's not changing this value. I'm refining it. I could actually fix these 2 and now refine only 1 value. And even doesn't want to change it. Okay, let's keep them, okay, as they are. I think this is now a reasonable fit, okay? Actually, it's a nice fit. So now let's go to any arbitrary peak. Let's go to a peak here and say, oh, if now I covered everything for my fundamental parameters, this peak should fit perfectly without any refinement, right? So let me just fix this one here. Oops. Can't see the mouse anymore. Okay, let's fix it. And also fix, I think I already fixed the receiving slit here. I fixed it at 0.1. Probably I should, let me go back and just refine it and see if I get an improvement. Yeah, 0.12, okay, it's probably right. So let's fix it there, okay? Now I have a really nice fit. Everything is fixed. So I go to an arbitrary peak, let's say this one here, and put in another peak. Go to my peaks phase. Click off, I don't want any crystallite size. And if everything would be perfect, if we live in a perfect world, and if I covered everything, that should give a perfect fit. Is this a perfect fit? Well, yeah, it's a fit, but it's not a perfect fit. It probably covers the actual divergence pretty nice, but there is some problem. The peak is broader. Why is it broader? Yeah, because there's no other optical elements. Yeah, it's the parallax. This is something which drove me personally quite crazy for some time. Yeah, how to handle this parallax effect. Actually, there's one option Alan Coelho put in, and it's taking care of parallax. You can say there's a position-sensitive detector, but since we're using 3 detectors here, this particular correction is not working perfectly. So we just simulate the parallax effect. And I figured out, and there's also a paper by Maidenhall and from NIST, it's basically a tension theta dependence of a Gaussian or a rectangular peak shape. So in this case, yeah, we would go in here to additional convolutions and say, okay, add a convolution, and now we can add whatever we want. Yeah, you can in the script mode, it's called launch mode. Yeah, you can type in now any formula you want. I had a student once typing in a formula which went over 2 A4 pages, and it works. Yeah, which is amazing. Yeah, you cannot do it here in the GUI, but that's not what we need. We can just say, what do we want to fit in here? And I say, ups, I want the Gaussian peak. Well, it's one peak, so it doesn't matter if it's constant or not, but I already say there should be a tension theta dependency. And the value, I think I've no idea. Let's refine it. And let's see, oops, and this works pretty well. Okay, wow, that's a good fit. It's about 0.12. Okay, fine. So let's assume I covered the parallax. That would mean now I can go now to any peak I want in the pattern and not refining anything, and every peak should be fitted, let's say, satisfactory or acceptable. Yeah. So let's go to a peak up here. Yeah, let's go to this peak and say, okay, put in a peak, peak space. Okay, we will skip some parts, so that's okay. Let's get rid of, because we don't want any crystallite size or strain. And if I now press this one, and if I did a good job, it should be a good fit. I think it's a pretty good fit. It's not a perfect fit, because you're not refining the entire powder pattern. But it's just from first principles, it's fitting, yeah? So we can take any peak we want, even the ones which are up here somewhere. I mean, let's use, I don't know, use this one here. Yeah, do the same thing, put in another peak, not refining anything, just fit it. Yeah, it's not perfect. So that means there is some dependency, yeah, which I'm not taking care completely, but almost. So, and of course you don't do single peak fitting. You do single peak fitting the very first time you do the instrumental resolution function, because you want to figure out if the parameters and the assumptions are working for the peaks. But then, of course, you do the entire fit. And there are the two possibilities. One is you use a polyfit, which is basically, or a Lemay fit, which is nothing else than the Rietveld without structure. Yeah. So you start from intensity 1 and you just have the intensities as variables in there. But the shape, the curve, or the powder pattern, yeah, is then fitted. Or you do the Rietveld. And since we are running out of time, so I think what we can do now is I just load in now the one I've prepared, and we just go through them. So I don't have to do it, I have to type in everything by myself. So I say File, I close this completely, I go to the project file, and the download thing is here somewhere, Bernd, or the where we put it? Local PC downloads here.
Good.
Yeah, and there must be somewhere my subdirectory. Was it in downloads? I've done. Bernd put it somewhere. Documents, downloads. I don't know. Let's see. I don't see it here. We need it in any. No, maybe it's documents. Yeah, it's in documents. Okay, good. Found it. Instrumental resolution function. You see, for you to exercise, there is the old beam 16 from ESRF. There is a copper Bragg-Pentano D8. There's a molybdenum D8 Dinnebier. There's a copper Dinnebier D8. Yeah, there are neutron data. There's some old Philips machine. There's a Rigaco copper machine. There's a Stoa silver, Stoa copper, Stoa molybdenum, and the Wombat neutron in Australia. So they're all instrumental resolution files to try, test, to work with. You don't have to go through all, but maybe 2 or 3 of them. And we are here at the Stoa one, and so the Stoa one is the molybdenum. And you see, this is the fundamental parameters. It's the same pattern we have seen before. And the only difference is here, now I'm defining the entire pattern. And I put in a peak in here. Why did I put in a peak in here? Because there's this hump from the background. And you can see it much better if you use the square root. I always never look in a linear scale at a powder pattern. I always use the square root, because then I see the small peaks better, okay? And let's just do the refinement, and that's the Rietveld. Okay, and now we can actually go to the difference curve. So this is the same we did before, but now for the entire powder pattern, and we put in the structure, and the structure you find here. First of all, you see this is the same wavelengths, yeah? The background, I'm using quite a few parameters because I was just trying. We can use 10 or 9. Here it was shooting 18 because it's behaving well. We can look at the background. This is the background. So now the gray curve here shows the background. The instrument, we have the receiving slit, and ours refined in 1 peak to 1.22, and it's here it refines to 1.14. It's probably correct. Yeah, and this is the actual model, the 3 parameters. Then the correction here is so small, I didn't even refine it. I can put it in, yeah. The Lorentz polarization factor we have already. Yeah, the peaks phase is just the background. You see the crystal size is 1.1 nanometer. This is why this green peak extends over a big portion of the entire powder pattern, okay? And we put in, this is now different, not a single phase, we put in the structure, and this is the lanthanum hexaboride structure. And you see, this is what we do when we now do structure divination the next, after the coffee break. So what you put in is the space group, the A parameter, because it's cubic, and then of course, since it's a Rietveld and it's a relative intensities, you have to refine the scale factor, right? That's actually all, the rest is calculated. And if you go to the microstructure, there's nothing, because this material is supposed to have no microstructure, which means infinite crystallite size and no strain. If you go to Andy Fitch's beamline, the ID22, and do the probably best and highest resolution powder pad in the world, within this standard, you find out there's a remaining strain component. And you can also directly determine exactly the crystallite size. So these effects are there, but not for you in a laboratory. You have no chance to see it, okay? but the world is usually a little bit more complicated than we see it, okay? I'm just saying there's nothing I'm refining here. So the question is what I'm refining. This is what I showed you before. This is the, oops, let me go up the instrument. So I'm refining the 3 parameters for the actual divergence, which is only refining the asymmetry. I'm refining the width of the receiving slit. And in the additional convolution, what I showed you, which is mimicking the parallax effect, the Gaussian tangents theta. And that's it. And again, I mean, this is a very, very, very good fit. Yeah. What makes the fit a bit challenging is they're 3 detectors and they have to be aligned within the thousands of degrees. And yeah, but you can do it.
Yes. Where did you apply error?
Oh, this is the additional convolution. So since there is no direct command in TOPAS for the parallax, there's an indirect one. Yeah, so you can put in a position sensitive detector, but this works well for a single position sensitive detector, which is not too broad. Yeah, but since we are using 3 detectors in a row, yeah, the whole thing is a little bit more complex. And therefore, I use from the paper from Medenhall, I use, he said it's actually a tension theta, whatever dependence on something. And you put it in here and you see in TOPAS, you can put in any additional correction. Yeah. And then it's done. Yeah. It's not a strain. Yeah. Because a Gaussian tension theta dependence, you can easily misplace with a strain. Yeah. But if you put in a strain, it would be wrong. Yeah. So therefore, we put it into additional convolutions.
But by any instrument.
Yes. In the instrument, or what you later would do, you would not put it in the instrument. You would actually, I think, put it somewhere here in the global parameters. Yeah. Because this is then really your instrument. This is not the instrument only for this particular powder pattern. Yeah. You would do it in a general way. Yeah. So I said it's a tree structure. So once you have this, you take the numbers and put them in the channel one, then you store it, and then it's in the global parameters whenever you call that particular profile, okay? PRO, yeah? But I did it not in the global one, I did it here in the one layer down just for this particular pattern, okay? And what else is interesting here? Let's go down here. 5 minutes, perfect. So what else is interesting here is when we now go, so this is a lantern hexaboid already Rietveld, so therefore somewhere there must be a structure. So we go to the sites, and now the sites tell you the atoms. And that's something really interesting because you have the lanthanum and the boron, right? And when we take a look at the structure, we can click on the lanthanum hexaboride and say, view the structure. This is the structure. Yeah. You see, these are the lanthanum atoms, and these are the boron atoms. And interestingly, yeah, so the lanthanum is at 0, 0, 0, so at the origin, and the boron is something like approximately 0.2, which is refined, so therefore it's red. And now you see it's not saying refined, it's just saying this at sign, and the half and the half, yeah. But now you see something very odd here. Yeah, the boron has an occupancy of 1.1. Cannot be, right? So let's correct this and refine the 2 Debye-Waller factors. And now I do the refinement. And what do you see here? What's wrong? Question to you, to the audience. What cannot be? I'm right. Lanthanum is this tiny little atom with no scattering power. Is that correct? How many electrons has lanthanum? Who knows it? Free coffee. Who's the first? Something like it's about 57, right? So this is a fat B, right? This, no? And boron is 5. Yeah, it's nothing. Yeah. And now you can say, okay, can it be that the light boron has a smaller Debye-Waller factor than the big lanthanum? No. Even it would be polarized. And the reason is this is partly ionic. Now you can say, okay, 5 borons, Okay, but this is not one boron, this is a cluster of 6. So 6 times 5 electrons is 30 electrons, right? The lanthanum is 3 plus. So then it should be actually not 30 electrons, but if I take 3 electrons away from the lanthanum and give it to the boron cluster, then the boron cluster has not 30 electrons, but 33. 33 means this would be 1.1 the occupancy of the boron, right? Because if you divide it and then say 5 electrons, this is 1.1. And so if I put in here one, I mean, don't ever publish anything like this here. Don't send a zip file to Acta Chris and say, oh, my boron is an occupancy of 1.1. But I'm just saying you how precise these measurements are if you have a highly crystalline material in powder diffraction, you measure over the entire range. I mean, lanthanum hexaboride is unique, okay? But how precise these things are. So I put in 1.1. And now it's correct. Yeah, this is about right. It's about the values. It's actually almost the values from the single crystal analysis. Okay.